Welcome back. It's Chapter 14 and 15, Part 2, Introduction to Inference. We're talking about statistical inference. Two of the most common types of statistical inference. Confidence intervals. In other words, we're going to estimate a value. What is the population mean? And test of significance, otherwise known as hypothesis testing. Is the population mean smaller, larger, or different than a certain value? Now, both types of inferences are based on the sampling distributions of the statistic in question. Now, in Chapter 14 and 15, we're going to start with a setting that is somewhat unrealistic. It's simplistic, but it will help make the reasoning behind these statistical techniques much easier. These conditions must be met. First of all, the sample that we have has to be obtained by a simple random sample. That's number one. We have a simple random sample from the population of interest. There is no non-response or other practical difficulty. Number two, the variable we measure has an exactly normal distribution. That is, it's normally distributed with a mean of mu and a standard deviation of sigma in the population, or the sample size is 30 or more so that the central limit theorem can be evoked for the sampling distribution. That is, that the sampling distribution of the sample mean must be normally distributed or approximately normally distributed. Number three, we do not know the population mean, but we do know what the population standard deviation is, sigma. So, simple random samples to obtain our sample, that our sampling distribution has to be approximately normally distributed. And number three, that sigma is known. Only under specific conditions can confidence intervals or significance tests be trusted. In other words, that they'd be reliable. Like I said, you can always plug numbers into formulas, but if these conditions aren't met, those numbers that result are unreliable. So you must understand the conditions that must be met, and you must judge whether they fit your specific problem. Inference is most reliable when the data comes from a random sample or a randomized comparative experiment. Random samples use chance to choose respondents. Randomized comparative experiments use chance to assign subjects to treatments. The deliberate use of chance ensures the laws of probability apply to the outcomes, and this ensures that statistical inference makes sense. So the data must come from simple random sample from the population. In other words, you should ask, where did the data come from? Different methods are needed for different designs. The Z procedures are not correct for samples other than simple random samples. Outliers can distort the results. The sample mean is strongly influenced by outliers. Always explore your data before performing an analysis. You want to make sure that you do not have outliers and that you have normality. The shape of the population distribution does matter. Skewness and outliers make Z procedures untrustworthy unless we can evoke the central limit theorem. In other words, that our sample sizes are large enough. And remember, in Stat 250, we picked the number 30, that our sample sizes have to be greater than or equal to 30. As I said, that's not necessarily always the case. It really depends on the parent distribution. But in our class, we're going to choose 30 or more so that we can evoke the central limit theorem. In practice, the Z procedures are reasonably accurate for any sample of at least a moderate size from a fairly symmetric distribution. The population standard deviation, that is sigma, must be known. Unfortunately, sigma is rarely known, so Z procedures are rarely useful. Chapter 17 will introduce procedures for when sigma is unknown. Where did the data come from? When you use statistical inference, you're acting as if your data are a probability sample or come from a randomized experiment. Statistical confidence intervals and tests, that is, when we estimate or test a value, those cannot remedy basic flaws in producing the data, such as voluntary response samples or uncontrolled experiments. Also, be aware of non-response or dropouts in a well-designed study. If the data do not come from a probability sample or a randomized experiment, the conclusions may be open to challenge. To answer the challenge, ask whether the data can be trusted as a basis for the conclusions of the study. So in other words, make sure our 3 conditions are met and you'll be fine. Remember, in this section we assume that we know the standard deviation of the population, that's sigma. This is not very realistic, but we need it for right now. So let's review sampling distributions of the sample mean once again. Shape: normal provided the population is normal, or it can be normal if we have a sample size large enough so we can evoke the central limit theorem. So it could be approximately normal if the sample sizes are large, that is, n greater than or equal to 30. This is always true, that the mean of the sampling distribution equals the mean of the population, and the standard error, or the standard deviation of the sampling distribution of the sample mean for samples of size n, always equals the standard deviation of the population divided by the square root of the sample size. Now, we know from the empirical rule that between 2 standard deviations from the mean, 95% of our data lie. And when we use Table A, our standard normal table, we can get more specific that 95% of our data lie between 1.96 standard deviations from the mean. Thus, if you think about that, if you had a sampling distribution, the sample mean, the mean of the sampling distribution is within plus or minus 1.96 sigma divided by the square root of n of the population mean, 95% of the time. So if we took a sample of size n, found the mean, it would probably 95% of the time would lie in between plus or minus 1.96 sigma divided by the square root of square root of n, approximately speaking. So we can flip this around because there's that relationship between the sampling distribution's mean and the population mean. If the sample mean is within plus or minus 1.96 sigma divided by the square root of n of the population mean 95% of the time, then we can flip this around to say that the population mean is within plus or minus 1.96 sigma divided by the square root of n of the sampling distribution's mean 95% of the time. So that we can say x bar is between mu minus 1.96 sigma over the square root of n and between mu plus 1.96 sigma divided by the square root of n. And that's the same as the population mean being in between the sample mean minus 1.96 sigma over the square root of n and the sample mean plus this product, 1.96 times the standard deviation divided by the square root of n. So what does that give us? That is 95% confidence intervals for the population mean are going to look like you take your sample mean and then you add and subtract to it. You create a range of values by doing this. You find the left endpoint, x bar minus 1.96 sigma over the square root of n, and x bar plus 1.96 sigma over the square root of n. And that would give us a range of values that are potentially our population mean could be within. And in fact, if we do this enough times over and over and over again, and we create intervals like this, about 95% of those intervals truly will contain the population mean. So what you just see up there, this x bar plus or minus, and then what the thing behind the plus or minus 1.96 sigma over the square root of n, this is the form, the point estimate, that's your x bar, and the margin of error. The margin of error is your critical value times your standard error. The critical value is obtained by what confidence level you're at. We wanted a 95, so getting the 95 confidence interval about the mean gave us the 1.96. We'll learn all the other ones in just a while, in just a couple of minutes. So in the next installment, we're going to see how this will help us to create a confidence interval.